Prove that the magnetic field induction at a point. Prove that the magnetic field induction at a point due to a current flowing through a long straight conductor, due to a current flowing through a long straight conductor is B equal mu 0 by 4 pi, mu 0 divided by 4 pi into 2I by R using Ampere's circuital law. Using Ampere's circuital law, we can draw a long straight conductor. XY is the long straight conductor through which a current I flows, and a circular magnetic field line is produced due to flow of current I through the long straight conductor. This circle is the magnetic field line which is produced due to the current I flowing through the long straight conductor XY. This is the magnetic field line, and this is an imaginary line, and this is also known as circular closed path around the current I. That means the current I is threading at right angle to this circular closed path or circular magnetic field line. O is the center of this circular magnetic field line, and we consider the radius of this circular magnetic field line as R, and P is a point on this circular magnetic field line. R is the radius of this circular magnetic field line. We consider a small element on the magnetic field line. Here A and C are the 2 points, and AC be the small element of length dl. dl is the length of the small element AC on the magnetic field line around the point P, and at the point P, length vector, that is vector dl, acts tangentially and inwards. Also, the magnetic field induction at the point P due to the current I flowing through the long straight conductor is B, and this magnetic field induction, that is vector B, acts inwards. Let R be the radius of a circular magnetic field line. R be the radius of a circular magnetic field line around a long straight conductor carrying a current I. Around a long straight conductor XY carrying a current I. Let R be the radius of a circular magnetic field line around a long straight conductor XY carrying a current I. dl be the length of the small element AC. dl be the length of the small element AC on this circular magnetic field line around the point P. dl be the length of the small element AC on the circular magnetic field line, and vector dl acts tangentially. Vector dl acts tangentially to this circular magnetic field line. Vector dl acts tangentially to this circular magnetic field line. According to Ampere's circuital law, the line integral of magnetic field induction under bracket vector B, the line integral of the magnetic field induction, under bracket vector B over the circular closed path or over the circular magnetic field line, is given by closed integration vector B dot vector dl is equal to mu 0 times of current I. The surrounding medium is vacuum and having permeability mu 0, where I is the current which is threading the circular magnetic field line, at right angle to it, or closed integration B.dl cos theta equal mu 0 I, where vector B is parallel to vector dl, and angle between the direction of vector B and vector dl is 0 degree, theta equal to 0 degree, and magnetic field vector B acts tangentially in an inwards, and small length vector dl is also act tangentially and inwards. That's why magnetic field induction vector B is parallel to vector dl, and angle between them, that is theta, is equal to 0 degree. Under bracket of vector B, we can denote a cross sign that indicates that magnetic field induction acts inwards. Or comma close integration B.dl cos 0 degree equal mu 0 I. Or comma close integration B.dl is equal to mu 0 I. Now this magnetic field B is uniform over the circular magnetic field line. That's why this magnetic field B can be brought outside. So B close integration dl is equal mu 0 I. Where the magnetic field line, where the magnetic field induction under bracket vector B at all the points on the circular magnetic field line, is uniform. Circular magnetic field line has constant value, and in the diagram, so here B is constant. That's why the B can be brought outside integration, and we get B integration dl equal mu 0 I. If we consider a point P1, and magnetic field induction at P1 is B1, and at the point P, magnetic field induction is B. So now B1 is equal to B, means magnetic field inductions at the point P1 and P on this circular magnetic field line will be same, B1 equal B. That's why magnetic field induction B is constant, and here again we can consider the diagram. Or comma B 2 pi r is equal mu 0 I, where closed integration dl is equal to 2 pi r. Closed integration dl equal to 2 pi r. Closed integration dl equal to 2 pi r, which is the circumference of the circular magnetic field line around the long straight conductor xy. Closed integration dl equal to 2 pi r, which is the circumference of the circular magnetic field line around the conductor xy. Or comma B equal mu 0 I divided by 2 pi r. Or comma B equal to mu 0 by 4 pi dot 2I divided by r. Dot 2I divided by r. So B equal mu 0 by 4 pi 2I by r. This is the magnetic field induction at a distance r from a long straight conductor xy carrying a current I. This is the magnetic field induction. This is the magnetic field induction at the point P. This is the magnetic field induction at the point P at a distance r from a long straight conductor xy. From the long straight conductor xy. B equal mu 0 by 4 pi 2I by r. Therefore, at the point P on the circular magnetic field line, magnetic field induction is vector B, which acts inwards and which has the expression B equal mu 0 by 4 pi 2I by r. And we get the expression of magnetic field induction at a point due to a current flowing through a long straight conductor, and it acts inwards. So we get B equal mu 0 by 4 pi 2I by r. And this is the magnetic field induction. This is the magnetic field induction at the point P at a distance r, from a long straight conductor xy carrying a current